A solenoid valve is a vital component in countless systems. It acts as an automated gatekeeper. Its job is to control the flow of liquids or gases. This control is achieved through an electromechanical process. A small electric current activates a coil. This magnetic force moves an internal part. The movement either opens a pathway for fluid to pass or closes it to stop the flow. These devices are incredibly common. You find them in industrial machinery, irrigation systems, household appliances. Their widespread use is due to their reliability simplicity. They allow for precise, automated, and remote control over fluid dynamics, which is essential for modern engineering and infrastructure management. The importance of choosing the correct solenoid valve cannot be overstated. A mismatch can lead to system failure. It could cause leaks, incorrect flow rates, complete stoppage. At its core, a solenoid valve is a simple yet ingenious device. It combines electrical energy, mechanical action to manage fluid flow. The central component is the solenoid itself. This consists of a coil of wire wrapped around a hollow tube. Inside this tube sits a movable ferromagnetic plunger called a core, called an armature. When an electric current is passed through the coil, it generates a magnetic field. That magnetic field exerts a force on the plunger, causing it to move up, causing it to move down. This movement is the key to the valve's operation. The plunger is connected to a seal connected to a disc that blocks or unblocks an orifice in the valve body. The process is remarkably direct. When the coil is de-energized, there is no magnetic field. A spring typically holds the plunger in a default position, keeping the valve open, keeping the valve closed. This is known as a normally closed configuration. A pilot-operated solenoid valve, also known as an indirect acting valve, is a smart design. It uses the pressure of the fluid within the system to do the heavy lifting. Instead of relying on the solenoid's magnetic force to open the main valve directly, it uses that force to control a much smaller, secondary passage. This small passage is called the pilot orifice. When the solenoid is energized, its plunger lifts a small seal, opening this pilot orifice. This action releases the pressure from the top of a flexible diaphragm or piston that is holding the main valve seal closed. This pressure change creates an imbalance. The higher pressure from the inlet side of the valve can now easily lift the diaphragm or piston. This chain reaction allows a small amount of electrical energy to control a very large flow. The solenoid only needs enough power to open the tiny pilot orifice, not to lift the entire main seal against the full force of the system pressure. This design makes pilot-operated valves extremely energy efficient, especially for larger pipe sizes. They are commonly used for pipes with large diameters, with sizes available up to 14 inches, DN 350. However, this design has a critical requirement. It needs a minimum pressure differential between the valve's inlet and outlet ports. A direct-acting solenoid valve operates on a much simpler principle. The force generated by the electromagnetic coil is used to move the main valve seal directly. There is no pilot orifice or diaphragm involved. When the coil is energized, the magnetic field it creates pulls the plunger upwards. This plunger is physically attached to the valve seal, or it may be the seal itself. As the plunger moves, it directly lifts the seal off the valve seat, opening the orifice and allowing the fluid to flow. When the power is cut, the magnetic field disappears, and a spring pushes the plunger and seal back down, closing the valve and stopping the flow. This direct mechanism means the valve's operation is completely independent of the system's line pressure. It can function perfectly from zero pressure all the way up to its maximum rated pressure. This makes direct-acting valves incredibly versatile for a wide range of scenarios, especially where pressure is low, especially where pressure is variable or non-existent. However, this direct action comes at a cost. The solenoid coil must be powerful enough to overcome both the spring force and the force exerted by the system pressure against the seal. This requirement for a more powerful coil results in higher energy consumption compared to a pilot-operated valve controlling a similar flow. It also limits the practical size of the valve. Because the coil's power limits the size of the orifice it can open against system pressure, direct-acting valves are typically found in smaller sizes. When you need to purchase a solenoid valve in Jordan, there are several reputable local suppliers who can provide products, technical expertise, and after-sales support. Working with a local supplier is often beneficial. They understand local standards and regulations. They can also offer faster delivery times and readily available spare parts, which is crucial for minimizing downtime during maintenance or repairs. Many of these suppliers act as official agents for major international brands. Choosing the correct solenoid valve is a straightforward process. Follow a few logical steps. First, the pipe diameter. This often guides you to the correct valve type. Large pipe, over 1 inch. Choose a pilot-operated valve. It's energy efficient at larger sizes and lower cost for big diameters, ideal for high-volume applications. Small pipe, 1 inch or less. Consider a direct-acting valve, especially if pressure is uncertain or very low. The physical constraints of valve types make this a critical filter. For wastewater treatment plants, specify as follows. Service: municipal wastewater service. Industrial wastewater, abrasive solids and particles. Fibrous content, 2–4% suspended solids. Function: on-off isolation. Function: automated dosing. Fail-safe spring return operation. Normally closed by default, direct acting for DN25 and below. 1 inch and smaller pilot operated for above DN25. Minimum differential pressure 0.3 bar sizes DN15 to DN80 standard. Larger sizes available on request. Provide KV or CV for each size. Body material 316 stainless steel for corrosion resistance. Body material PVCU for chemical duty. Body material CPVC body material PP coated ductile iron acceptable for non-chemical lines. Seals: EPDM for wastewater and chlorinated water. Seals: FKM for oils and solvents. Seals: PTFE for aggressive chemistry. Pressure rating: typical 0 to 6 bar for wastewater lines. Specify maximum working pressure and test to 1.5 times that temperature. Fluid 5 to 60 degrees Celsius standard. High temperature options available on request. Coil: 24 VDC or 230 VAC power options. Coil: Class H insulation. Coil: IP65 minimum, IP67 preferred. Coil DIN 43650 connector and strain relief. Power: E-Adoctant 12 WDC or E18 VA AC for direct acting valves. Pilot operated power per manufacturer datasheet. Duty cycle: 100% ED continuous with thermal protection enclosure, weatherproof enclosure, ATEX or IESEX XD or XM where hazardous zones apply. Flow path: full port where clogging risk exists, include anti-clog geometry or lifted seat design. Filtration: install a 500 micron strainer upstream, include a flush or bleed port connections. BSP or NPT threaded for DN25 and below PN16 flanged for DN32 and above. Use gaskets compatible with the media. Mounting: coil vertical up preferred. Include a manual override position indicator with no and NC limit switches. Compliance: CE and RoHS RAS or NSF for potable lines where applicable. Life cycle: at least 1 million actuations for direct acting. Life cycle: at least 2 million for pilot-operated maintenance. Toolless coil change. Maintenance: accessible seat supply, a spare seal kit and spare coil. Documentation: provide datasheet. Documentation: IOM, installation, operation, and maintenance. Documentation: wiring diagram. Documentation: ATEX certificate if applicable. Documentation: warranty of 12 months or more.